Now we're going to talk about positive definite matrices. This is section 3.4, and this is quite an important section, so I suggest you pay attention carefully and even read the book. So we're going to be in the setting of a finite dimensional vector space, and for all intents and purposes, let's take Rn, and we're interested in inner products on Rn, and more or less the question is, what are all of them? So, for example, in R2, we've seen that besides the dot product, another example that we talked about is you can take the inner product to be given by x, y, x prime, y prime is equal to any number a times xx prime plus any number b times y, y prime, provided a and b are greater than 0. You need the greater than 0 for positivity. But that's not all of them. We've seen other examples, and let's try and figure out what all of the possibilities are. Well, let's just think about R2 for a minute. And if you think about it, if you have any inner product, the bilinear property says that the inner product of x and y together with x prime and y prime, what kind of formula is allowed? Well, we saw up here, for example, you're allowed to take x prime times some constant a, and well, so xx prime was here, xx prime, but you can also take y prime, so that would be plus a term xy prime, b xy prime, and then similarly c y x prime, and then finally d y y prime. So that is to say, you're allowed to take either x or y and multiply it by either x prime or y prime. There's 4 possibilities, and you're allowed to put arbitrary constants in front. And it's a basic fact that that any bilinear inner product is of this form. So, for example, you're never allowed to have something involving an x squared or any other kind of function of x. This is the only formulas which are allowed, and maybe you should pause the video for a moment and think about that. Why is that true? It's not hard to see. So let's go on. And so that's the bilinear condition. What about symmetry? Well, let's see. If you switch x and x prime, this term stays the same, and when you switch y and y prime, this term stays the same, except when you switch x and x prime, if you switch them, this becomes x prime y, which is this term, and so it switches those terms, and symmetry holds exactly if b is equal to c. And there's a very nice matrix way to write this, which is to write this formula, which is the following. You write it like this. It's x, y times the matrix A, B, C, D times x prime, y prime. And let's stare at this for a second. So here I'm multiplying a 1 by 2 vector times a 2 by 2. And when I multiply these, I'm going to get a a 1 by 2 vector, and then when I multiply it times this, I'm going to get a number. Well, let's just see that. So if you do this first multiplication, what you get is ax plus cy, and then you get bx plus dy, and then you're multiplying that by x prime, y prime, and when you multiply this kind of vector times this kind of vector, you get a number. You get ax plus cy times x prime plus bx plus dy times y prime, and if I'm lucky, that's this formula: axx prime, cyx prime, bxy prime, and dyyy prime. So that's indeed equal to this. Okay, so, well, I said that the symmetry condition is that B is equal to C. So let's plug that in here. And you see that this matrix, which I'll call K, K is symmetric. Right, which is to say that K is equal to K transpose. So let's see what we just said. So again, what I have now is that I can write it this way: that I've defined the inner product of V and W to be V transpose times K times W, where K is this 2 by 2 matrix, symmetric matrix A, B, B, C, or excuse me, D. And I'm writing V and W as column matrices. So V transpose is a row and W is a column, and that's just another way of writing what I had on the previous slide. And, well, I did this for R2, but this clearly works in Rn. So let's summarize what I just said. Suppose you're working in Rn, and you have an inner product. Then the inner product of two vectors is given by this formula. Oops, I forgot the transpose here. V transpose K W for some n by n symmetric matrix K. Okay, so let's think about this for a minute. So well, we're not quite done, but this is a big step of the way towards describing every inner product. The fact that it's bilinear means it has to be given by an equation like this, and the fact that it's symmetric is taken care of. So we have bilinear is taken care of, and symmetric is taken care of. But what about positive? It's obviously, I could take, if I took K to be minus 1, that would not be positive. But it's not so easy to tell when it is positive. And so basically, we just punt. Definition. We say K, symmetric matrix, is positive definite so that's the main concept in this section, is positive definite if V transpose K, V is greater than or equal to 0 for all V. And also that it's equal to 0 only if the vector is the 0 vector. So this is one of these definitions that's kind of a cheat. Something's positive definite if it satisfies the condition that you need it to satisfy. How do you tell? So I've basically defined, in other words, I've defined this notion so that I'll just squeeze it in down here. I've basically just proven that the bilinear forms are exactly the same thing as K's, which are n by n. So this is bilinear forms, of course, on Rn. K's, which are n by n, symmetric, and positive definite. And again, the reason that this is sort of a cheat is, well, the n by n and symmetric are clear, but I basically just defined positive definite to make this true. So we need to talk a little bit more about positive definite and how you tell. All right, so notice that the positive definite condition is a condition on this number V transpose K V. And, well, that's VV. If this is, in fact, does define a bilinear form, if this is positive. And this is, of course, the length of V squared. And, well, we just have a new name for this. So this is a little definition. If you're given a K, we define a quadratic form on Rn. K, everything's Rn, n by n, of course. We define a quadratic form on Rn to be the following function: Q of V, or if you want to indicate the dependence on K, you write Q sub K of V, is this V transpose K V. Or, in other words, it's simply the norm of V squared. So, I mean, we don't really need it because we don't really need this new terminology because we already have the norm, but this is standard terminology, and so anyway, it's just a new word for something that we're already familiar with. And let me write this out in coordinates. This says that Q of x1 through xn is the summation over all I and j of k, I, j, x, I, x, j, where the matrix K is given by the kij's are the entries in the matrix. So this is the sum over n squared terms, and we part of the definition is we say the quadratic form Q is positive definite if this function Q of V is greater than or equal to 0 for all v, and equal to 0 only if v equals 0. So it's just corresponds exactly to the notion of positive definite form. In other words, what I just said is that K is positive definite if and only if its quadratic form, Q sub K, is positive definite. So I've barely said anything. I'm just sort of restating things over and over again. The quadratic form is positive definite if only if this thing, no matter what K, the Kij's are fixed, and no matter what Xi's and Xj's you plug in, you're always supposed to get a positive number. All right, well, the only hope I have of understanding this is to look at a 2x2 example. So let's suppose we had a 2x2 matrix, and I'll write it now as A, B, B, C. And this is my matrix K, and I want to know when this is positive definite. So the condition is that A, x squared, plus 2b xy plus cy squared is supposed to be greater than or equal to 0 for all x and y. So, I mean, it's really greater than or equal to 0 and only equal to 0 if blah, 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 but never mind. How do you tell this? So no matter what x and y I plug in here, I'm supposed to get a positive number. Well, if b was equal to 0, then it would be easy because you'd have ax squared plus cy squared, and the only possibility would be if a and c are greater than 0. But if b is not equal to 0, it's complicated, and it's not necessarily that b is positive or anything like that. So let's simplify this, and part of the problem here is the two variables, x and y. So what if I just pretended it was one variable? So I took y to be 1, say. I'd have the single equation like this for all x, and this is something a little more familiar. It's a single quadratic equation in x, and it's a parabola, and if you put on your Math 140 hat, you'll remember that a nice way to think of this is to complete the square. Complete the square. And I know everybody here remembers how to complete the square, so you don't need to pause the video and go back and remind yourself how to do that, unless you do need to, in which case I recommend you do that. And when you complete the square on this thing, what you get is a times x plus b over a squared plus ac minus b squared over a is supposed to be greater than 0. All right, why is this any better? So this is supposed to be, I'm trying to understand the condition that this thing holds for all x. Well, this is a little bit easier to understand because this term is always positive. So that, what does that tell you? Well, I claim that this holds if and only if, first of all, a had better be bigger than 0. Because if a was less than 0, well, that's clear. If a was less than 0, this is a negative number. And, well, this could be a positive number, but if you let x go to infinity, this is a bigger and bigger negative number. And so eventually this whole thing would become negative. So you certainly have to have that a is bigger than 0. And And another condition is, for example, you could take, if you take x is equal to minus b over a, then this term is equal to 0. This term, it becomes equal to 0, and so you'd also better have ac minus b squared over a is greater than 0. And so let me summarize that. K is positive definite if and only if a is bigger than 0, and secondly, ac minus b squared is greater than 0. And here I don't need to divide by a because a is positive, so the positivity of this, you can get rid of the a. So that's the condition for a 2 by 2 matrix to be positive definite. It's not entirely elementary. Now notice that AC minus B squared, by the way, is the determinant. So that's a natural condition. The determinant has to be positive, and then you also need that A is positive. All right, well, let's write this down again. So our matrix K is A, B, B, C, and the positive definite condition is that A is bigger than 0, and the determinant is bigger than 0. And remember where the determinant is AC minus B squared. So this is very useful for writing down some examples. So let's write down some examples. Let's say, so let's take A to be 1. So that's positive. We've passed this test, the first test. And you notice that even if I take C and B and C to be positive, this is not positive definite because the determinant is 1 minus 4 is equal to minus 3. So that's a reminder that positive definite is, oops, I wanted to do that in red, is not the same as all entries are positive. Okay, let's do another example. Well, let's see again. Let's take 1 here. Notice that C has to be positive also, because if C wasn't positive, this would be negative, and this would be negative, and that would be negative. So you have to take C to be positive. So I don't know, let's take C to be 4. And then the condition on B is that 4 minus B squared had better be positive, which is to say that B squared had better be less than 4, which says that the absolute value of B had better be less than 2. So this matrix 1, 1, 1, 4 is positive definite, but, excuse me, 1, 3, 3, 4 is not. Okay, I apologize. I see this is going to be quite a long lecture, but there's one more thing I need to cover. I'll try and get through it pretty quickly, and maybe I can say more about it in class. So we've been talking about Rn and what it means to have a bilinear form on Rn, which is to say a positive definite symmetric matrix K. What about an abstract vector space, V? How do you say what it means to have a bilinear form on an abstract vector space? Well, the key point here is something that I mentioned about a week ago, which is that if you have an abstract vector space V and you pick a basis V1 through Vn is a basis, then you can think of V, you can say V really is Rn, where the is in quotes. Depends what the meaning of is. And what I mean is that any vector in V is uniquely expressed as a linear combination of the basis vectors. And you think of this element as being equal, in quotes, to the n-tuple A1 through An. And anything you do in Rn having to do with explicit n-tuples, you can rephrase in the language of an abstract vector space in terms of these sums, and just keep in mind that in order to do that, you need to have chosen a basis. So everything I'm going to say depends on a choice here of a basis. So in the case of bilinear forms, what does that mean? So suppose you have a vector space V and a bilinear form on it. Here's the main definition. You pick a basis V1 through Vn, an arbitrary basis of the vector space, and then you say that the gram matrix of this inner form of V, of the inner product, and it depends on the choice of basis, with respect to this choice of basis, is the following matrix. You put V1, 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 V2, dot, V1, Vn, and so on. In the ijth place, you put the inner product of Vi and Vj, and so this is an n by n symmetric matrix. And it's symmetric because, well, I'll put the V2, V1 here, for example. If you look at these corresponding elements, one of them is V1, V2, and the opposite one is V2, V1. And basically, this is K. So let me summarize this in a theorem. Suppose you have a vector space V and a basis V1 through Vn. And I'll state this two parts of this theorem. So one is if you have an inner product, a given inner product, then you let K be the associated gram matrix, the one that I just mentioned with the inner products in it. So let K be the corresponding gram matrix. then the formula for this inner product is the following. It's just like what we had before, A1 V1 plus dot 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 AN VN inner product with B1 V1 plus dot 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 BN VN is nothing but A1 AN times K times B1 BN. So in other words, on this abstract vector space V, once you've chosen a basis, you can think of it as being Rn, and so now you have vectors in Rn, and the corresponding matrix of the form is this Gram matrix. And I should remind you, this is the matrix of inner products Vi, Vj. And in particular, since I assumed that I was given an inner form, so K is symmetric and positive definite. And part B is going to be going the other way, which is, suppose I'm not given an inner form, but I'm just given K, which is an n by n symmetric positive definite matrix. And given this basis, this formula, I'll just indicate this formula here. This formula defines an inner product. And so that is to say, what do I mean? I just give you a matrix, and then you define a function on pairs of vectors by this formula. If you take a pair of vectors, you compute a number like this, and that is an inner product. So that is to say that on this abstract vector space on V, an inner product, I'll say it this way, the collection of inner products is exactly the same thing, or I shouldn't say exactly the same thing, it's in one-to-one correspondence with, or it's essentially the same thing as the set of K's, which are n by n symmetric positive definite matrices. And but this correspondence here depends crucially on the fact that you have a choice of a basis. And let me just squeeze one last statement in here. And I'll talk about this in class, but let me get it up on the video. Fact is, if you have a K with respect to one basis, and you take a different basis, then the new K is going to be of the form K prime is equal to A K A transpose. So choosing a different basis amounts to modifying this K by this operation. And one way to remember this formula is that this matrix is still symmetric. Notice that A, K, A transpose is equal to, well, you switch the order and take the transpose, you get A, K transpose, A transpose, and K is symmetric, so you get A, K, A transpose. So that confirms that this is a reasonable thing to say. This is supposed to be symmetric, and it is. And it gives you a way to remember this formula, because if you multiply on the left by A and the right by A transpose, that preserves the property of being symmetric. Okay, one final comment about this is my explanation of the Gram matrix is not exactly the way he says it in the book. It's one of these things that's equivalent, but I'm thinking about things in a slightly different way. So I strongly recommend you look in the book and see the presentation in the book, and tomorrow I'll talk about this some more. See you in class.